Hello everyone. We are going to now begin our lecture on the chi-squared goodness of fit test. Now this kind of study is performed on qualitative data. That means data that comes to us in the form of names. Previously we've worked with numerical data. That means data that was given to us as numbers, and therefore we could take measurements on that kind of data, and we found the mean and the standard deviations and so on, and we performed our study, the related study, to analyze the data and draw inferences from. All right. But for qualitative data, the data that comes to us in names, we cannot take measurements on names. We cannot find the mean or the standard deviation of a bunch of names. So there's a special test for that can be used to analyze that kind of data. It's called the chi-squared goodness of fit test, and there's another one called the test of association or independence, which we will learn in another section of this chapter. Now, chi-squared is a new distribution that we are going to learn first before going into what the goodness of fit test is about. Just like we had the z distribution and the t distribution that was applied on studies of numerical data, for qualitative data, we will be using the chi-squared distribution. All right, so we will begin our lesson starting with what the chi-squared distribution is. So these are mainly the three topics we will cover in three sections. One is the chi-squared distribution. That's the first section of this chapter, where we'll first discuss the distribution, and it's pretty different from the z and the t distribution that we learned before. There are some parts that are the same, similar, but the nature of the distribution is somewhat different. Then once we understand the distribution, we'll go into what the goodness of fit test is, and then we'll go into the chi-square independence test in the last section of this chapter, which talks about the association between two variables. So it's going to be two-dimensional data, so to speak. Okay. Now this is what the chi-squared curve looks like. You have here three different curves, a blue one, a green one, and an orange one. And each of these curves have degrees of freedom associated with them. The blue one has df5, the green one has df10, and then the orange one has df19, which kind of looks similar to a normal curve, maybe a z or a t curve, but it is not one of that. All right, it gets to that shape, but it is a different distribution. It's a chi-squared curve. Now note some features about the chi-squared curves. These curves are anchored at 0. That means the lowest point on the left hand side, the lowest value of these curves is at 0. The lowest value is 0. We cannot have negative values, like remember how the z curve looked like. The standard normal curve had 0 at the center. All right, and then we had values of 1, 2, and 3. 1, 2, and 3 on the right hand side, and -1 and -2 and -3 on the left hand side. In chi-squared curve, this is completely missing. There are no negative values in chi-squared curves. What happens is the curves, the lowest point in a curve is 0 on the left hand side, and the curves rise from 0, as in this picture here. They rise from 0, that's the lowest point. They go up, they peak, and they drop down, and they get closer and closer to the x-axis as they go towards the right, but it never quite touches the x-axis, or it doesn't go below the x-axis. All right, that which is similar to how the normal curves, they never get below, or they never touch the x-axis, but they get closer and closer to the x-axis. Same thing here. However, the chi-squared curves are anchored at 0, and there are no negative chi-squared values, so to speak. And another thing that we notice is that as the DEFs increase, the curves take the shape of a normal curve. but they are not the normal curve. Their endpoints are at 0, which is very different from what we know is in a normal curve. The other thing is that a chi-squared curve is a right skewed curve. So just remember that it's a right skewed curve and its peak is on the left hand side and it has a long tail to the right. That's what a right skewed curves are. So keep that in mind. They are not symmetrical, they are right skewed curves. Now here are some basic properties to know about the chi-squared curves. Property 1 says the total area under a chi-squared curve equals 1, which is the same as with any other curve. That means the chi-squared curve will cover 100% of the observations. So the proportions, the area under the curve equals 1. That's the total area under the curve. Property 2 says a chi-squared curve starts at 0, which we saw in the previous diagram. It's anchored at 0 on the horizontal axis and extends indefinitely to the right, approaching but never touching the horizontal axis. So we talked about that too in the previous slide. A chi-squared curve is right skewed. I already told you about that. It's right skewed. It is not symmetrical like the z curve or the t curve is. And property 4 is as the number of degrees of freedom becomes larger, chi-squared curves look increasingly like normal curves, but again, they are not normal curves. It only looks like a normal curve. Now this is how the chi-square table looks like. The table in your formula sheet may be a little bit different, but normally chi-square table is arranged with degrees of freedom on the extreme left hand side, and across on the top row will be the alpha values. So you have to first go to your specific df. The formula to calculate df is going to be slightly different depending on the study, whether it's a goodness of fit test or if it's a test of association. Based on that, the formula is going to be different for degrees of freedom calculation. But once you calculate the df and you come to this table, first look for the row which has your df and then go across to locate the alpha value. If you're doing a hypothesis test or confidence interval, it'll be these special values 0.1, 0.05, 0.025, 0.01. Those will be the alpha values you will be needing. And then come to the table, come into the body of the table to find the exact chi-squared value for that particular df and the particular alpha value. All right, so look at these questions here. Let's quickly go over a couple of them. It says here, for a chi-squared curve with df equals 10, determine chi-squared of 0.05, a chi-squared value whose area to the right is 0.05. Now keep in mind a chi-squared area will always be to the right because it's a right skewed test. Our alphas will be located to the right of our critical values or our p-values and so on. All right, so here we have 10, right? For 10 we have to go down all the way to 10, which is here, and then 0.05 is going to be right here. So the chi-squared value is 18.307. All right, so chi-squared of 0.05 is going to be 18.307. This is the value. For df10, if it's chi-squared 0.025, so it's the same row, 10 for df, and 0.025 is right here, so 20.483. If it's df4, as it says here, for df4 we will have to look across this row here. If its alpha is 0.05, it'll be a value of 9.488. All right, 9.488. An alpha value of 0.01, it's going to be 13.277. 13.277. All right, so that's how you're going to look up your table to find chi-square values.